Today's lesson is on carboxylic acids. Carboxylic acid group contains both the carbonyl and the hydroxyl group, and they're bonded to the same carbon. They are often written as COOH, although I prefer to draw out the full structure. Aliphatic acids have an alkyl group bonded to the carboxylic acid, and then aromatic acids such as benzoic acid will have an aryl group. A little bit later on in the semester, we'll talk about fatty acids, which are long-chain aliphatic acids. Okay, these are some common names. And these are some common acids. And many of these have names based on their original source. And here are some examples. The simplest carboxylic acid, which our R group is a hydrogen, that is called formic acid. And formic acid comes from a Latin word formica, meaning ant. This is very irritating, and it's what makes the bites of fire ants so painful. Formic acid is also present in bee stings. The poet Ogden Nash wrote a poem about formic acid. He said, "The ant has made himself illustrious through constant industry industrious. So what? Would you be calm and placid if you were full of formic acid?" Acetic acid, or in the IUPAC, ethanoic acid, is a major component of vinegar. And vinegar is about a 4 to 5% solution. And the name acetic comes from acetum. Propionic acid, or propanoic in the IUPAC, comes from two words, protos, meaning first, and pion, meaning fat. Propionic acid is a component of the breakdown of butter fat, and it is a compound that is responsible for the odor and flavor of Swiss cheese. Okay, next we have butyric acid, or butanoic in the IUPAC. Butyric comes from butyrum, meaning butter. Butyric acid is a compound also produced from the breakdown of butter fat, and it is found in rancid butter. It has a really terrible smelling odor. It smells like vomit, and there should be no doubt whether butter is rancid or not. You will know. Butyric acid is also produced in human body odor. If you've been around someone that hasn't showered for a while, they have a really strong odor. One of the components is butyric acid. It turns out that many dogs are able to smell very tiny amounts of butyric acid. This is what enables bloodhounds to track people and to enable dogs to find skiers buried under snow, for example. Okay, the next acid we have is valeric acid. This comes from a plant, the valerian root. Caproic acid is 6-carbon carboxylic acid. It's hexanoic acid in the IUPAC. And its name comes from Capricorn, which means goat. Okay, here's another one. This is salicylic acid. And salicylic acid's name comes from salix, which means willow. This was a compound that was isolated from willow bark and leaves, and it is used to make acetylsalicylic acid, which is aspirin. The ancient Romans recognized that you could chew on willow bark and leaves to relieve pain, and it was in the 1800s that the compound was isolated and identified. Salicylic acid itself is too corrosive to use for pain relief, and so it was derivatized into acetylsalicylic acid. Okay, these are some other common names. In the common nomenclature, we designate the 2 position as alpha, the 3 as beta, gamma, delta, and so forth. This would be alpha chloropropionic acid. You probably won't see this too much unless you look at very old literature. This would be called 2-chloropropanoic acid in the IUPAC. This is gamma aminobutyric acid, or GABA. It's a neurotransmitter. This is isovaleric acid. Okay, remember valeric acid, which is a straight 5-carbon chain. This is the branch chain. Okay, these are IUPAC names. Formic acid is also called methanoic acid. The United States tends to use the common names more often, whereas in Canada and Europe, they use the IUPAC. Acetic acid is ethanoic acid, and this is 2-cyclohexylpropanoic acid. One thing I want to point out here is that the carboxylic acid takes priority, and the carboxylic acid group is on carbon number 1. Okay, so this is 2-cyclohexylpropanoic acid. Carboxylic acids have priority over ketones, and so this is 2-oxo-3-propyl-butanoic acid. We just saw gamma aminobutyric acid. This is 4-aminobutanoic acid in the IUPAC. Okay, here we have 3-phenylpentanoic acid. Here we have 3-methylbutanoic acid, which is commonly called isovaleric. Okay, so systematically, we take the alkane name, we remove the E, and then we add the suffix oic acid. Okay, here are some unsaturated acids. Okay, so this is E-4-methyl-3-hexenoic acid. Okay, the 3 indicates the position of the double bond. Right, this is 3-phenyl-prop-2-enoic acid. That's the IUPAC, and then this is commonly called cinnamic acid. We do specify stereochemistry, EZRS, for example. Okay, here are some aromatic acids. Benzoic acid is accepted in the IUPAC. Systematically, this would be benzene carboxylic acid. Okay, here we have p-aminobenzoic acid or 4-aminobenzoic acid. Okay, we just saw salicylic acid. Systematically, this would be 2-hydroxybenzoic acid. 4-methylbenzoic acid, or p-toluic acid in the common nomenclature. Okay, this is alpha-naphthoic acid. In the IUPAC, it would be 1-naphthoic acid. The other isomer you could have would be 2-naphthoic acid, which would be here. Okay, we do need numbers, especially when two or more substituents are present. Okay, dicarboxylic acids are usually called by their common names, particularly in the United States. For the IUPAC name, we number the chain from the end closest to the substituent. Okay, so this has 1, 2, 3, 4, 5, 6. Okay, so that would be 3-bromohexane dioic acid. Okay, if we have a dicarboxylic acids, it's a dioic acid. In the common nomenclature, this is beta-bromoadipic acid. Hexane dioic acid is commonly called adipic acid. Okay, I'm just going to require you to know the common names. Okay, here's the structure of formic acid. Okay, the carbon is sp2 hybridized, and it is planar with nearly trigonal bond angles. Okay, approximately 120 degrees. You can see it's not quite 120 degrees. Okay, here are the bond lengths. Oops. The CO bond also lies in the plane, and it is eclipsed with the CO double bond. The COH angle is 106 degrees. Formic acid is stabilized by resonance. These are the two resonance structures. The major structure is the one without charge separation. Carboxylic acids have higher boiling points than most other functional groups of similar molecular weight. They have higher boiling points than similar alcohols. They can form hydrogen-bonded dimers, as shown here. These dimers are strong enough where, for the smaller carboxylic acids, they're actually intact even in the gas phase. Aliphatic acids with more than 8 carbons are solids at room temperature. Double bonds, especially cis, lower the melting point. The following acids all have 18 carbons. Stearic acid, okay, there's no double bonds. Its melting point is 72 degrees. Oleic acid has one cis double bond. It's actually between carbons 9 and 10. You can see there's a significant drop in the melting point, 16 degrees. With room temperature being 25 degrees, this, of course, is a liquid at room temperature. Linoleic acid has 2 cis double bonds, one between 9 and 10, the other one between 12 and 13, and it melts at -5 Celsius. Water solubility decreases with the length of the carbon chain. With up to 4 carbons, the acid is completely miscible in water. Carboxylic acids are very soluble in alcohols, and of course solubility goes down in water as the length of the carbon chain increases. Carboxylic acids are also soluble in relatively nonpolar solvents like chloroform, because the hydrogen bonds of the dimer are not disrupted by the nonpolar solvent. Okay, one of the most notable properties of carboxylic acids is their acidity. And we can quantify the acidity by this factor called the Ka, which is the acid dissociation equilibrium constant. Okay, this products over reactants. We leave out pure liquids and pure solids, so we omit the water. The larger the Ka, the stronger the acid. The smaller the pKa, the stronger the acid. pKa is minus the log of the Ka. And carboxylic acids partially dissociate in water to give a proton and a carboxylate ion. They are weak acids. The equilibrium constant Ka for this reaction is called the acid dissociation constant. The acid will be mostly dissociated if the pH of the solution is higher than the pKa of the acid. Okay, so here we have an energy diagram for the dissociation of alcohols versus carboxylic acids. And we can see that the activation energy is much smaller for the carboxylic acid because the carboxylate is fully resonance stabilized, whereas the alkoxide has no resonance stabilization. In the acetate ion structure, the negative charge is shared equally between the two oxygens. Each oxygen bears half the negative charge. The delocalization of the negative charge over the two oxygens makes the acetate ion more stable than the alkoxide ion. Okay, some of the factors that can affect acidity include a nearby electronegative element, such as a chlorine. Okay, if we compare acetic acid with chlorinated acetic acids, acetic acid has a pKa of 4.74. If we substitute one of the hydrogens with a chlorine, the chlorine, by its electron withdrawing effect, will help stabilize the carboxylate ion. Its pKa is 2.86. Okay, so that's roughly 2 pKa units, so about 100 times more acidic. Dichloroacetic acid is even more acidic, and then trichloroacetic acid. Okay, that's a difference of 4 pKa units, so this is 10,000 times more acidic. Okay, we also see that the distance of the electron withdrawing group from the carboxylic acid group can affect the acidity. Okay, so here's 2-chlorobutanoic acid, and you can see that this ethyl has almost no effect compared to chloroacetic acid. Okay, but if we move the chlorine farther away, we can see that the effect is diminished, and by the time we get to the fourth carbon, the effect is almost completely absent. Substituents on an aromatic ring, especially at the ortho and para positions, can affect the acidity of benzoic acids. Okay, here's benzoic acid. We'll use that as a reference, 4.19. The paramethoxy. Methoxy is actually an electron donating group, so that's going to make it less acidic. A orthonitro. Okay, here the nitro is strongly electron withdrawing, and it's closer to the carboxylic acid group, and so that has a significant effect. Okay, this is now about 100 times more acidic than benzoic. And the P-nitro and M-nitro also increase the acidity, but not as much. Here is a table summarizing the acidities of various carboxylic acids. Okay, trifluoroacetic, fluorine being more electronegative than chlorine has a greater effect. The nitro group, strongly electron withdrawing, so nitroacetic acid. The nitro group significantly increases the acidity, as does a cyano group. Bromo has an effect, but but less pronounced, as does iodo. And here's benzoic acid. And if we get farther away from the benzene ring, we can see that acidity goes down slightly. Okay, I'm going to go ahead and stop here, and we'll look at deprotonation of carboxylic acids next.